Welcome you all to this video where we discuss unit 6 is about on numerical methods is about interpolation. Content of unit 6 contains two basic components. One is the Newton divided difference interpolation polynomial that covers in section 18.1, and second is Lagrange interpolation polynomial. So if we look at the interpolation, basically we have some data sets. Now we can do the regression on this that we discuss in unit 5. Now in this unit we will look at the interpolation. Interpolation is actually to fit a curve or a function that passes through all the points. So this is the main difference between regression and interpolation. In regression we actually look for closely matching the points, but in interpolation we want it to be pass from all the points. So quickly look at the motivation behind this interpolation. For example, if you have a data set, if you want to find some point that is not available in your data set, how you do that? For example, in case if you want to find sine of 0.15 and table didn't show you that, so in that case we use interpolation to do that. So the true value and the interpolation value is almost near. So this is the main idea behind this interpolation technique. Now if we look at interpolation, there's a basic idea behind is that in linear interpretation you need 2 points to fit the linear interpretation. So for example, if you have a 2 points, so you can fit a linear interpretation. If you have a 3 points, then this is quadratic in fitting. So this is the basic rule that normally we use. So look here, if from there we understand the general formula for interpolation that says that if you have nth order polynomial, then you need n plus 1 points to fit that nth order polynomial. Now there's only one straight line in case of first order polynomial. In second we have a parabola that connects it, and similarly if we have n plus 1 point, then we need nth order polynomial to fit it. Now let's start with the first one technique, that is Newton divide difference interpolation polynomial. So Newton divide difference interpolation polynomial is among the most popular and useful forms. So we have linear, quadratic and general form of Newton's interpolating polynomials. So error, we will look how error is calculated for Newton's interpolation polynomial. Now for example, the idea is very simple here. So what we did actually, we use a slope here. If you look at the figure on your right, we use the slope information to come up with this formula. So formula is that if we look at a point at x0 and similarly look at point x1, so these 2 points they are same on the same line. So based on this we come up with the solution, and that is that f1 of x minus f x0 is divided by x minus x0. Okay, so this is actually the slope. Okay, now what we did here is in the graph we took a point x that is in between 2 points x0 and x1. So we use this information and we say that if we are looking the slope between x0 and x1, because if you look on the right you have the same right angle triangle with same slope, so slope must be similar to points between x and x1. So we just write the slope value here. So first one is x1 f of x1 minus f of x0. This is the height, and divided by x minus x0. Similarly for second case we have x1 minus x0 and divided by x minus. So this is only slope. So we say that we have equal slope. So this is the basic idea. So from this idea we come up with this formula and we call it as Newton difference formula for linear case. Why it is linear? Because if we know that x0 is a constant. Similarly, if we look at the second term, that is f of x1 minus, is also another constant, but x is unknown. So it becomes a linear equation like this: f1 of x equal to b0 plus b1 x minus x0. So that's why it is called linear interpolation. Now we move to an example. Just look at how we can apply this thing. So the idea is to estimate the natural log of 2 using linear interpolation. First, perform the computation of the interpolation between log of 1 equal to 0 and log of 6 equal to 1.791759. Then repeat the procedure but use a smaller that log. So the idea is that we have 2 points. First we have to apply between 0 and 6. Other we have to apply between 0 and 4. So we are interested to calculate the logarithmic value of 2 that is not available with our data set. So how we do that? So what we did, we just calculate the true value, and the true value is 0.6931472. Now we just apply this formula, and now in first case we apply between log of 1 and 6. So what we get here, we just plug the values. F of f0 is 0. Similarly, f of x1, that is log of 6, is 1.7. So just we plug the values and we come up with f1 of 2. Okay, so in that case the error, relative error is, percentage of relative error is 48.3. It's much larger. Now for second case, that is between 1 and 4, when we do that, we have value of 0.46. Now in this case error is less. So the idea here is that as you have a narrow interval, you have better error calculations. So this is the basic idea about this linear interpolation. So look here in the figure, you have a linear estimate and you have the true value. So the value that is generated between 0 and 4 is better than 0 and 6. So this is the main idea. Now Newton divided difference interpolation is most popular. We have linear, quadratic and general form. Okay, now we also have error. So let's move to the next one, which is the quadratic form. So here I told you that quadratic is of second order polynomial. You need 3 points to do that. So this is the formulation, general formulation of quadratic equation, where b0, b1, b2. Okay, now here what is b0? B0 is your f0 of x. Similarly, what is b1? B1 is the difference between points x1 and x0. Okay, so how you calculate the slope between these 2 points is f of x1 minus x0 divided by x1 minus x0. Similarly, you have b2. B2 is now including 3 points that start from x0 to x2. So what we do actually here, we take the difference between x2 and x1, and then we subtract it between x1 and x0. Okay, and divided by x2 minus x0, because we have a point that is starting from x0 to x2. So this is the basic idea behind this. So if you look here, because we have x2 and x0, so this is in the division. So this is the main idea. Now let's do the same example. Now we need 3 points, so we use 1, 4 and 6 and see how this will perform. Just plug the value for b0 and b1 and b2. When we do that, we come up with the solution of 5.565844. So it's looking much better than the previous example with linear. So its relative error is 18.4%. So look here, it is also shown here that you have quadratic is much near to the true value. Now we can fill a table for this difference. So for example, if we have points here 0, 1, 2, there are 3 points, x0, x1, x2, and then we have a function values of f of x0, x1, x2. This is the first 3 parts of the table. The next one is the first difference. First difference you have to take between x0 and x1. Similarly between x1 and x2. So you just plug here. Then you take another difference, you get the second. So this is the table that you can fill with the Newton quadratic interpolation technique. So look here, if we do same thing for the previous example. So if you remember, we got 1, 4, 6, 3 points. So these are the values. So we take the difference between these two divided by 4 minus 1. So we come up with this value. Now we have to take the difference here in between these two. So divided by 2, we come up with this, and then we have to take difference between two. When we take the difference between these two, now 3 points are involved. So in that case, we have to take 6 minus 1. So divided by this difference, we come up with this value. So this is the way you can easily calculate this table, and from this table you can easily apply the formula. Look here, we have B0 and B1. Similarly, B2. Now let's do an example just to understand how it works. For example, if we have this information with us, so f of x value is given to us. Now we can take the first difference. So how we do it, just using this. So for first difference, we have minus 3 minus 5. So it is between first 2 points, so 1 minus 0. Similarly, if you look at the second point, so we have to take the difference between 15 and 3, minus 15 and minus 3, and then take difference between 1 and minus 1. So when we do that, we come up with 6. Okay. Now we have to take, we have to write the third column. For third column, we have to move to this one. Here we have to take the difference between 6 and 2, but here points involved is 0 and minus 1. So this is the main catch, that you have to be careful which points are involved here. So this is a very good illustrative example. Now we just plug the values and we come up with the solution. So this is the way you can write this. So the first row actually tells you the coefficient values of your interpolation function. Now let's see how this behaves. Now what we did here is that we just have an example here. Now what we did here, we just swapped the numbers. Okay, so for example, in first data set we have initial point is 1, 2 and 3. In second, the value we have 1, 2, 3 here, and output value is 0, 3, 8. So what we did here in the second example, we just swap it. It means that we start 2, 1, 3, and we want to see how this affect on the interpolation. So the question is that, do interpolation is affected by swapping the numbers? Now in first case and the second case, we get the same result. So the idea is that interpolation is independent of swapping the numbers. Okay. So ordering the point should not affect the interpolation polynomial. Now we have to go to general form of Newton interpolation polynomial, and then we will look for the error. Now general form, for n plus 1 we have nth order, so we can write this general form of the equation. Okay. Now here we know B0 is this, B1 is this, similarly B2 is this, and Bn is actually between n and x0, and that has involved xn to x1, then n minus 1. So this is the main formula that we have for Newton difference interpolation. Now let's do an example for third order. So now for third order we need 4 points. So look here, we have 4 points here. Now we just plug the formula here and just calculate B0, B1, B2 and B3. So when we do that, because we know that B0 is actually the actual system, so we need to start from B1 and B2 and B3. So we just do it. So here what we get here, so this is the final equation that where we plug the values. Now when we do that, the value is 0.6287686. So look at 9.3% error was recorded. So if we fill the table, we can do that similarly as we did in previous example. Okay. Now Newton's divide difference interpolating polynomial is among the most popular and useful form. The last bit here is errors. Okay, how to calculate the error is very, very important. Now for errors, the equation of interpolating polynomial is similar to the Taylor series, as we know that it is extracted from Taylor series. So we normally calculate the error by capturing the higher order behavior of underlying function. So the idea is that this is R, and the residual of if you have nth order polynomial that fits for the point, so you have to go for n plus 1. So this is the basic remainder formula. So from this formula we know that we have to calculate the n plus 1 difference between 0 and then multiply with the points from x0 to n. So we come up with the residuals. For example, estimate error for natural log 2 using second order polynomial. How we do that? So this is the main idea. We just find out the x3. Okay, so we have 0 to 3, and we just want to apply this into this. When we do that, we get R2 values. It's around 0.069248. Similarly, if you have this table, okay, so from here, if I ask you to find the find a polynomial to interpolate the data, so what you do, you know that from this we have information like this is our first value, this is first difference. Okay, so we have to use this row to write the equation. How we do that? Look here, the first element that we pick is the 3 1 here, then is the second difference. Okay, so this is the one. Okay, similarly we have this value and the loss value, so we use this value actually to come up with the solution, right? This is with the first one. Okay, this is the b0, b1, b2, b3 and b4. All right, so this is the way you can use your table to calculate the difference. Now Lagrange interpolation polynomials, the last bit of this is the Lagrange. So Lagrange just rearrange the points. He is now calculating in terms of function value. You want to calculate in terms of x value. So the idea is that reformulate the Newton method. So this was the Newton method. So what we did actually, we just rewrite it. Okay, so when we do that, just take the LCM and just do that. So it's just very easy. Now this formula is very easy to remember. For example, x minus 1, x naught minus 1, so we have x naught. We have x1 minus 1, so we have f of x1, x minus x naught. So this is the main idea that we can use to calculate difference, right? Now if I move to next slide. So if what we did here is that we come up with a function that is summation. So look at these are two sums of Lagrange multiplied with f of x. So for example, if I is 0, so we are talking about this one. If I is 1, we are talking about this function, and so on. Now these points x minus x1 divided by x minus is defined by this L term. Okay, so Lagrangian term, because this is the Lagrange interpolation, so that's why we use L capital L to represent them. So it says that this is actually a multiplier. Okay, what are the multipliers? That j equal to 0 to n is x minus xj times xi minus xj. So this is the main idea where you can calculate the points. Now the Lagrange will to reformulate the Newton formula. So we come up with this one. Okay, now similarly here we have to find the remainder, so which is almost the same. Okay. Now let's do an example to understand this concept very clearly. So we want to find the log of 2 first and second order using Lagrange interpolation. So these are the points that are given to us. Now we have to apply Lagrange method. So Lagrange method is based on this formula, that is x minus x1. So these are L terms and we have f of x naught and x1. Just plug the values. For second order we have 3 points, so we have 3 components in part of Lagrange. Now when we plug the values, for first value is 0.4620981, for second one is 0.5, so it's much near, close to the original value. So the idea is that whenever you have this polynomial in Lagrange, so the idea was that for each point you have a different function. So you just combine those functions, you come up with interpolation. So this is the main idea, main crust of this. Okay, now this is for you. You just have to practice this question. So question is that we have data given to us, and we have to estimate f of 4 using Lagrange interpolation first, and then using Newton's interpolation polynomial. So this is the Lagrange one. Now we have to move, because they are we move to Newton's method. Newton's method is from B0 plus B1 B2. So this is the formula. So we need to just plug in the values and we calculate it. So it is a good question to practice yourself. So this is the actual answer. And thank you for. So that's it for this unit. Okay.